Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside and we are concluding Chapter 7. It's done. It's finished after the end of this video, where we go to the Chapter 7 test and cumulative assessment in the Big Ideas Math Integrated Math 2 textbook. It is a series of a single page for the Chapter 7 test bit, I think it generally is, and then a 2 pages front back kind of thing. If you want to download these separately in the PDF section, or description section down below, find the PDFs down there, and you can take a look at what I'm going to be looking at with you guys doing these problems, where they get a nice mixed variety of things. If I remember to do so, I will tell you which sections things look like they're coming out of from this Chapter 7 stuff. It can be a little confusing because like even 7.5 on trapezoids and kites also touch on things like rectangles, rhombuses, squares, and parallelograms and things like that, so maybe I can't. But guys, let's just go ahead and go into it. I am ready if you're ready. I'm going to start writing a 1 because I assume a 1 is what's coming up, yes. And they have no examples leading into things, so it's just a problem set. Probably going to go kind of fast with these. If I can talk while I write, that's fine, but otherwise we're doing it. Number 1, find the value of each variable in the parallelogram. They tell you it's a parallelogram, so we're going to go based off of that. R is going to be 6. Now this is because diagonals bisect each other in a parallelogram, so those two parts are equal here. And then these two parts will be equal, S and 3.5, so S is also 3.5 with that in mind. That's number 1. Cool. Number 2. In a parallelogram, opposite angles are congruent, so B is going to be the same as this one, and A will be the supplement of that value. So B will be 101, A will be 180 minus 101, whether you do it from B or the 101 that's there, and that is 79. Number 3, opposite sides of a parallelogram are congruent, so those measures will be equal. So I can set P is equal to 5 straight up, and Q minus 3 equals 6, so Q will be equal to 9. Very, very fast problems to begin with there. Let's see how swimmingly the rest of them go. Numbers 4 through 6, we're going to give the most specific name for the quadrilateral and explain our reasoning. No, because it looks like it, and I almost wish in some ways they didn't make it look like the one that it's probably going to be, so you make your best guess. In other words, if I gave, on number 4, if I gave the look like this, boom, and I said, boom, tell me what it is, a lot of people might say square, a lot of people might say rectangle. But go off the markings that I have. I have right angles here. There's nothing that says these need to be right angles. Exhibit A, number 4's visual version of what they're showing you. And I think the important part here is mentioning if I have right angles here, then they're supplementary. They're not just congruent. 90 plus 90 is 180. They're supplementary, which means these lines are parallel. But I know nothing about these lines being parallel, and that's the important part. What is this? It's a trapezoid. That's the best name that I know to give it. It's a trapezoid because one set of parallel lines, one pair of parallel lines based on the converse of the same side interior angles theorem. And again, just based on that drawing alone, based on the markings of the drawing, we can say that. So there's number 4. Number 5. Once again, they're giving you a visual of like, well, not just making it look like a square or anything like that, which you could almost imagine it's one, but then you show these are congruent to each other. And then these in their own way are congruent to each other here. Sets of consecutive sides that are congruent, 2 different pairs of them, and they're uniquely congruent. Right angle or not, this is a kite. I don't know if it's called a right kite or something like that, but this is a kite. Doesn't matter about that right angle. This is 2 pairs of consecutive sides that are uniquely congruent. Now, if all of the sides were congruent to each other, it would be a rhombus. If opposite sides were congruent, it would be a parallelogram. They're consecutive sides that are congruent. Now, number 6 is the same kind of thing. I have unique sets of angles that are congruent, and of course they give the appearance of the diagram as well, so you might be able to know what this thing is. But be careful on this answer. It's not just what you think. It's not just a trapezoid. It is a trapezoid. It's not just a trapezoid. It's an isosceles trapezoid. Now, how do we know that it must be a trapezoid just with this information? Why can we say that here? Well, being a quadrilateral, it needs to still add to 360 degrees. So when you have two ones that are congruent here and two that are congruent, like here, let's just put it this way. Two of the same x's plus two of the same y's have to equal 360, right? If these are both, instead of doing what I just marked here, let's call these x's and y's. X, x, okay, those would be the same, right? And y, y. 2x's plus 2y's have to equal 360. If I divide by 2, then x plus y is to equal 180. If those have to be supplementary, that means that these lines have to be parallel. Again, same reason for number 4. So we will have parallel lines there. This will be a trapezoid. With the angles congruent in that way, base angles, this will be an isosceles trapezoid here. Once again, one set of parallel sides. One set of parallel sides. And base angles congruent. All right. So these questions, guys, would have been probably out of section, and I didn't mention before, these probably would have been out of section 7.5. And the questions before that in the parallelogram, probably 7.2. If they said what would make it a parallelogram, it would be 7.3 likely. But in the parallelogram, 7.2. A bit slower for questions because we had to explain some things. Number 7. In a convex octagon, now this is not out of 7.5. This sounds like 7.1 automatically, 7.1. In a convex octagon, 3 of the exterior angles have a measure of x degrees. The other 5 exterior angles have a measure of 2x plus 7 degrees. Find the measure of each exterior angle. So 3 of them have measure of x degrees, x plus x plus x. Let me just say 3x. 3x is there. Now we're going to add, these are exterior, we're going to add 5 angles that have a measure of 2x plus 7. So let me do this. Not 3x in parentheses, but 3 times x. 3 x's plus 5 of those. And these are, it doesn't matter that it's an octagon, other than that there are 8 angles. Doesn't change the exterior angle sum, which is still 360. Let's kind of distribute here. We'll get 10x plus 35. And sorry, I'm just doing algebra from here. 325 and x equals. Now this problem looks very familiar. It might be part of my "Are you ready?" thing. I didn't make that one, so maybe they got the question from here. I don't know if this is exactly the same. It looks very familiar. The only problem is I still don't know this division. So 130, 260, plus another 65. I think that's 25. Yes, I think this is the same question. So x is 25. But it says find the measure of each exterior angle. So x is 25 is the measure of 3 of them. That's one set. I almost feel like this is how I wrote this. The other set, second set, will be 2 times 25 plus 7, which is 57. So 25 degrees and 57 degrees. Sorry the way that I kind of wrote the answers there. It's kind of hard to answer that part afterward, but yeah, 25 and 57. All right, that's number 7. Yes, that looks identical to that other question. I don't know if the numbers are the same, but the kind of question there. So if you want to check that out and hear the exact same thing in another set, go to the Are You Ready quiz review thing that I did. Number 8, quadrilateral PQRS has these vertices. Classify this quadrilateral using the most specific name. This could be from that review. I have no idea. Now, they do say quadrilateral. They do not say parallelogram. So if I do find out it's a parallelogram, then that can help address easier ways to find out rectangle, rhombus, square, things like that. But P is at 5.1. Q is at 9.6. R is at 5.11. Ooh, up there. And S is at 1.6. PQRS. Now, my first go-to with this one, I actually want to go based off the diagonals, and I think that'll address a lot of what we have to say on it. That can address things within a parallelogram as well. Parallelograms diagonals bisect each other, and I can work off that. Listen, there are a lot of ways I can do this problem, right? I'll probably talk about some of the other methods, but the diagonals are vertical and horizontal. Definitely one of my loving go-tos because it's just a count, nothing more. So the count, not just the full diagonal, but even half of it, assuming it's half. 1, 2, 3, 4, 5. This part is 5, and this part is also 5. That means this diagonal is bisected by this. This is 1, 2, 3, 4, and 1, 2, 3, 4. Okay, this tells me a lot. The diagonals bisect each other. That makes it a parallelogram. However, being vertical and horizontal, the diagonals are also perpendicular to each other. That makes it a rhombus and a parallelogram, right? It's a rhombus because of the bisected part being a parallelogram, but the perpendicular part makes it therefore a rhombus more specifically. It's not a rectangle because the diagonals aren't congruent. Boom, boom, not the same. This length is 10, this length is 8. Diagonals are not congruent, therefore it's also not a square. This is a rhombus. The diagonals are perpendicular bisectors of each other. Perpendicular bisectors of each other. Now, what's another way I could figure out it's a rhombus? I could do the side lengths. This would have then gone over 4, up 5, left 4, down 5, and 5 and 4. All sides would be congruent side lengths. If you're curious, 5 squared, 4 squared, root 41. These would have all been root 41. I can't somehow write the number 41 very well, except for right there, but that also would have showed you that you had a rhombus. And there's number 8. Whoops. I need to change this page, not that page. Number 9. 9 through 11. Determine, before I do that, this probably would have been out of section 7.4, given that they also talk about rectangles, rhombuses, and squares, or they give you the thought of that, because the answer was rhombus. All right, number 9, determine whether enough information is given to show the quadrilateral is a parallelogram. Explain your reasoning. That sounds like 7.3. So on number 9, and I think this is more of a typed out kind of thing, so let me get the typing ready. On number 9, I have diagonals bisecting each other. That is indicative of a parallelogram indeed. Yes, parallelogram, because of the parallelogram diagonals converse. If the diagonals bisect each other in a quadrilateral, then that quadrilateral is a parallelogram. That's a reason. That reason is enough. Number 10. Number 10, I don't know what I have. I have a diagonal congruent to sets of sides. Those sets of sides are congruent to each other, but they're not parallel, and I know nothing about those other sides. I don't think that diagonal being congruent has anything to do with how this shape will mold itself and how the angles can do certain things. Not at all, in the slightest. Not enough information. I don't know how to tell you not enough information other than to show you. I'm going to show you a visual that I can do that would be different. Let's say I had a quadrilateral where there's that diagonal, right? It's congruent to this one here, and I can mend the angles, right? And then I can change this one to like that right there. These are all congruent to each other. By the way, I'll show you what I'm connecting in a bit. But these are all congruent to each other. Let's shrink the diagonal portion of it to like that. And now let's connect these dots. And then, boom, I made this shape. That's not a parallelogram. It's not a trapezoid. It's not nothing. Those being congruent doesn't change anything. And you're like, well, they drew it like this. Well, it doesn't matter how they drew it. It matters what's marked, right? I drew it like this. I drew the same things that are congruent like that. So, yeah, not enough information on number 10. And here's my reasoning. I'm disproving my counterexample there. Basically not one of the converse theorems. I would need to know that the opposite sides are parallel as well, or something. Anyway, let's move forward. Number 11. Yeah, so on number 11, listen, remember, we don't know it's a parallelogram, but the angles have to add to 360, the interior angle sum. So we can't say anything supplementary. We can't, well, actually we sort of can. We can say because these are supplementary, boom, then those are parallel, and therefore, because those are parallel, these will have to be supplementary. So I guess we can. You could either add to 360 and find out that's 60, or find out through supplementary means that's going to be 60. All sets of things are parallel, da-da-da. But we're not really going based off them being parallel. We're based off opposite angles being congruent. and supplementary and things like that. I mean, there are a lot of ways we can say that. Is this a parallelogram? Yes. Trying to say how my reasoning would work. So 11, yes, parallelogram, because of parallelogram opposite angles converse. I guess I'm good there. I talked about the parallel lines thing, converse of same side interior angle theorem and same side interior angle theorem, but I could have added these to 360 to find out that was 60. If the opposite angles are congruent, then it is a parallelogram. Number 11 is yes. Okay, number 12, explain why a parallelogram with one right angle must be a rectangle. I answered this in another review, probably the previous review. Why must this be a rectangle here with one right angle? Remember, they're not saying there is only one right angle, therefore it's how can we conclude all the others would be right angles? Because opposite sides are because let's see, a parallelogram with one right angle must be a rectangle because opposite angles in a parallelogram are congruent, which would make the opposite angle a parallelogram, and consecutive angles in a parallelogram are supplementary, and the supplement of 90 degrees is 90 degrees. 90 is 90, which would make them all right angles, and is the definition of a rectangle. All right, I'm going to kind of format that meanwhile so you can absorb what I said there. Yeah, if you have a parallel, now it needs to be known to be a parallelogram for this to work. You can't just say a quadrilateral with one right angle is a rectangle. No, because you could make the other ones different angles. But since opposite angles would have to be congruent in a parallelogram and consecutive would have to be supplementary, everything builds itself to be a rectangle based off that. I guess that's section 7.4 with that in mind. So is this one here. I'm not sure about 14 yet. Summarize the ways you can prove a quadrilateral is a square. Oh boy. I don't know if I know all of them. So number 13. If a quadrilateral has... Basically, you need to find ways that it's both a rectangle and a rhombus. So what makes a quadrilateral rectangle rhombus? If a quadrilateral has 4 right angles and 4 congruent sides, that's one way. I got to figure out how to best do this. If a quadrilateral's diagonals are perpendicular are congruent and perpendicular bisectors of each other, the congruent is something indicative of a rectangle. That doesn't mean all rectangles do that. If they bisected each other also, then it would be the perpendicular part. So the bisector part's parallelogram, the congruent part is rectangle, and the perpendicular, did I say that right? The bisector part's parallelogram, the congruent part is rectangle, and the perpendicular part is rhombus, with the bisecting part being parallelogram. So that and that, trying to think of what else we would actually make mention of. Diagonals, perpendicular. I'm just going to stick with that. There are probably other forms of things that you could do, but I think those are good ones. Those are good ones. Number 14. 3 vertices are of a parallelogram. So that sounds like 7-2. 3 vertices of a parallelogram are this. Find the coordinates of M. Find the coordinates of the intersection of the diagonals of JKLM. So, let's get a graph thing ready. I'll go in my faster approaches, given that I have the graph. Meaning counting slopes and things like that. So J is -2, -1. K is 0, 2. L is 4, 3. And they do call it JKLM. So J, K, and L connect all together from J to K and K to L. L and J would both connect to M. This is something I mentioned more about in the review portion. Now I'm kind of more doing. So let's work off of a slope. From K to J and from L to M should be the same kind of slope process, meaning how far down, how far over kind of thing. That's down 3 and left 2. So we can also go down 3 and left 2 like that. And this would give me the ordered pair for M to make it a parallelogram. Opposite sides would have to be parallel. You can see there that kind of has the parallelogram look. And they do say that it is a parallelogram. Parallelogram, J, K, L, M. So M is at 2, 0. Now they do also say find the coordinates of the intersection of the diagonals of parallelogram JKLM. Diagonals would intersect at each other's midpoints. From K to M, I think you can almost see within here that if you found the midpoint of this diagonal, it looks like it's going to be at 1, 1. From J to L, if I did the same thing, you also get that 1, 1. Your goal really here is just to find one of the midpoints of one of your things. So I'm going to find the midpoint from K to M from 0, 2 to 2, 0. That's down 2, right 2, or down 1, right 1. Yes, the midpoint would be at 1, 1. And remember, they're both the same midpoint. And I know I'm going through that in kind of a sloppy way. Average 2, 0, and 0, 2. 2 plus 0 divided by 2, and 0 plus 2 divided by 2. You get 1, 1. They are concurrent. Diagonals bisect each other, so they meet at each other's midpoints. That's going to be 1, 1. I didn't even try JL. I don't really need it. Midpoint of KM or JL. Okay. All right, that is number 14. That is section 7.2. That is parts A and B. So part A, part B. All right, number 15. You are building a plant stand with 3 equally spaced circular shelves, kind of as pictured, and then they have a diagram version. Shows a vertical cross-section of the plant stand. What is the diameter of the middle shelf? This is something out of trapezoids. This would be section 7.5. 7.5. So we're looking at the cross-section. We see the measures that you have here. When a trapezoid, when a trapezoid has a mid-segment drawn, that mid-segment is the average of your two bases. In this case, 6 and 15. We add them up and divide by 2. We take half of it. Half of 21, we are going to get 10.5. Now it's 10.5 inches. We have the inches there, so I'll just kind of leave it. No, they did say what's the diameter of the middle shelf. So 10.5 inches is the answer. Diameter. And that is number 15. Number 16. The Pentagon in Washington, D.C. is shaped like a regular pentagon. So any good old-fashioned pentagon, they mean all sides congruent, all angles congruent. I can actually generate one for you with my tool. So here's the Pentagon in Washington, D.C. Woo! Kind of. Find the measure of each interior angle. It doesn't matter if it's the one in Washington, D.C. or another regular pentagon. Just find the measure of here. So the interior angle sum of any polygon is 180 times the number of sides minus 2. Pentagon being a 5-sided shape. And 180 times 3 gives you 540 degrees. This is the interior angle sum. But each eye here being the same, being congruent, means there are 5 eyes there. So you take the 540 degree interior angle sum and divide it by 5, and you get 108 degrees. That is the interior angle sum of that. So if you go to a corner of the Pentagon and they don't think you're doing anything of sinister terrorist-like behavior by measuring the floor plan of it, they say, what are you doing? They say, I'm doing geometry, sir. I'm doing stuff out of section, what section? Wait, hold on. Out of section 7.1 in my Big Ideas Math IM2 textbook. Then that can answer it. Number 17, you are designing a binocular mount. I think it's the diagram here. If BC is always vertical, the binoculars will point in the same direction while they are raised and lowered for different viewers. How can you design the mount so BC is always vertical? Justify your answer. What? I get what they mean as far as the hinge thing, if I hinge it a certain way. I just don't know what they're asking. If BC is always vertical, they'll point in the same direction while they're raised and lowered for different viewers. They asked me how to design the mount. I mean, you want to make it a parallelogram-based thing. You want to make sure that AD is always vertical. You just want to make sure it's always a parallelogram, and these things hinge. I don't know how to really answer the question on 17. Make sure ABCD is a parallelogram, so the hinges on A and C will make the same angles always, and that D and B. I don't know if that makes sense. I don't know if you understand what kind of design this is. I'm not an engineer, but kind of I don't have anything here to use what I'm talking about. There's the binocular mount there. But if this thing could go up taller and stuff and stay vertical as long as this stays vertical and these things hinge in a certain way. I know exactly what to do with it. I just didn't know how to answer that question. I hope that that's enough. Just keep it in a parallelogram nature. If so, that's probably 7.2 question, 7.3 question. I'll say 7.3 more so. And number 18, this is just for the chapter test portion. Cumulative assessment comes next. The measure of one angle of a kite is 90 degrees. Kind of, maybe it's like this. The measure of another angle in a kite is 30 degrees. Sketch a kite that matches this description. Well, it could be very much like the kite thing that you see right there. And it just says one angle of the kite's 90 degrees, so I'm imagining no others are. Same with the 30. So sketch one. Yeah. Let's do very similarly to what they have there. If I have a 90-degree angle here, okay, 90 degree, and this side's maybe 30, like that. Maybe that's 30. Let's now extend that out. Boom, boom, like this. So this could take on the kite. And remember, with the kite, the sets of consecutive sides would be congruent and all that. So here's my 90. Here's my 30. These are congruent like this. So this could be the sketch. A little more so, let's figure out what those other angle measures would be if this were x and x. So 2x plus 90 and 30 would equal 360. I was about to say 180. 2x plus 120 is 360. 2x is 240, so x is 120 as well. So these would be 120-degree angle measures here and here for that to work out for the kite as well. So that's an example of that kite. And that works for me. And that is section 7.5. 7.5. Okay, that is the end of the chapter test portion for this. About a half hour in, and we have a cumulative assessment portion with only 8 questions, I believe. They stay short, but cumulative is everything from previous chapters as well. This is chapter, 7? So anything from chapter 1 onward can apply to these kinds of questions. Let's see what comes next. So let's go back and let's look at this set here. A lot of these tend to have like multiple choice. Oh, I take it back. That's not multiple choice. This is a lot of fill in the blank on this number 1. Let me copy and paste this. They say copy and complete the flowchart. So let's copy and paste this entire thing here. Make it easier for ourselves to fill in blanks for this flowchart proof, of which I have no idea that they're asking about yet. Still got to shrink it, it looks like. So for you to copy it down, sorry. You can print out my PDF if you need to. Okay. Given you have a parallelogram, prove that A is congruent to C and B is congruent to D. How are they going to prove B is congruent to... Oh, they do it here. 2 different flows of proofs. So given you have a parallelogram, they draw a diagonal BD by construction through any 2 points that exists exactly one line. Fantastic. AB is parallel to CD. AB is parallel to CD. And BC is parallel to AD. Very much so. You want to mark things up when you do that. This is the definition of a parallelogram. And that is what we get to write. Okay. ABD is congruent to CDB. ADB is congruent to ABD. Let's do different colors. ABD is congruent to CDB, and ADB is congruent to CBD. Now, notice that this is a flowchart proof. They went from parallel lines to here. Because the lines are parallel, we can say what we're about to say here. This is the alternate interior angle theorem. Because of parallel lines, alternate interior angles are congruent. Now, from there, we get to flow into two different portions. Let's start with the bottom one. BD is congruent to itself. That's this middle guy right here. This is the reflexive property of congruence. We have enough information now to show that these two triangles, this guy is congruent to this guy because angle, side, angle with angle, side, angle, triangle ABD congruent to triangle CDB by the angle, side, angle congruence theorem. Therefore, angle A is congruent to angle C by CPCTC. With these two triangles congruent, their corresponding parts are congruent. So CPCTC. This was a proof that they did in the past, and for me, I think I said, just draw the other diagonal for the other way. And totally would work, should work, could work. But they want to use the diagram once, they want to draw this thing once. So they're going to go based off the math of it all and say that with these angles being congruent, their measures will equal each other. This is known as the definition of congruence. Those angles are congruent, therefore their measures equal each other. Now they're about to say measure of angle B is the addition of these two angles. Measure of angle D is the addition of these two angles here. That's nothing more than the angle addition postulate. Angle addition postulate. Now notice which ones they have that add together. ABD with CBD, ABD with CBD, and ADB with CDB. Boom and boom. Now we have parts that are equal to each other. We have that mentioned right here. ABD is with CDB. So ABD could have been there, etc. So measure of angle B is equal to measure of angle D because of the things that are equal together as well. I assume this is the part that gets a little hard to work off of because they're skipping steps of substitution, but they're kind of transitioning from the things that are equal to plugging them in to then setting these things equal to each other. And in a substitution way, I believe this would be the transitive property of equality. That's the part that I might have a little trouble with acknowledging for sure, because I feel like a step or two is skipped in stating that, and sometimes I skip a step or two in stating the exact same thing there. And back to definition of congruence here, if measures are equal, then those parts are congruent. But remember, that's not the only way that you can do this. You could have drawn a new diagonal instead for AC and done the exact same thing. Angle, side, angle congruence in CPCTC, but that's going to work itself out. That is number one. This would have been from chapter 7. This would have been from chapter 7 because it's all about parallelograms. All right, let's go to number 2. Which function is represented by the graph? Now, unfortunately, I don't remember all my chapters anymore. I believe this is chapter 3. Oh, what are our chapters? We graph and then we solve. What was chapter 2? What was chapter 1? The absolute value stuff. Okay, chapter 2. So yeah, this is chapter 3. So chapter 3, which is represented by the graph, we're going strictly just based off, it's not going to be A or C because those have negative stretch factors. That parabola would have been upside down. Is it B versus D? You could try and plug in points, but the bottom line is if it was D, 4 times 1 squared would have been 4. It would have been up here like that. Tall stretch factor. This is compressed. You go over 4, you go up a quarter of 4 squared of 16, which is 4, like that. This is going to be B. Number 2 is going to be B. I'm just going to put here y equals 1/4 x squared. That's all. Number 3, account A as an initial balance of $1,000 and increases by $50 each year. Account B as an initial balance of $500 and increases by 10% each year. Will account A always have a greater balance than B? Explain. I think this is out of chapter 1. Now, I was going to say specifically what section. It's either chapter 1 or chapter. I think it's chapter 1. I was going to say even specifically what sections these were. I don't know if I remember the sections, unfortunately. Maybe 1.6 was the name of the section. Yeah, something like that. But you're comparing something linear to something exponential with this. So for account A, I'll call this A equals, no, let's see, let's do Y sub A. Account A equals, $1,000 is the initial amount, and then it adds $50 each year if X is number of years. Y sub B, the amount of dollars you make here, you start with $500, and it increases 1.1. You multiply by 1.1. That's the 10% each year for this number of years. That's to the X power, by the way. Now, I'm not really intent on showing graphing calculator stuff, but if I had a version of this graph, and by the way, they don't require you doing anything equation-wise or anything. This is what I'm doing to just give you a heads up on it. The $1,000 amount, if this were $1,000 right here, then it increases by $50 each year like that. For the 1,000, that's linear. What happens in this other scenario here for $500 though, is you start at 500, so it's less than, but a 10% each year is just going to show this jump. It's going to be taking off in some sort of way, and it's going to surpass it and keep going. This one's a curve, whereas the other one's a line. At some point, it will surpass it. It's a guarantee. As long as it's a growth, it could increase by 0.001% each year, and it might take thousands of years to surpass it, but eventually it will surpass it. It says to explain. Will account A always have a greater balance than account B? Explain. No. Account B will eventually surpass account A because an exponential function will always dominate a linear function over time if both have growth. It doesn't matter. Listen, it doesn't give us a time frame, and it didn't ask what time frame it was. If I used a graphing calculator and stuff, I could tell you exactly what it is. I have no idea. But over time, one will always beat the other if both are about growth. Or if both are about decay, one will surpass the other in the same kind of way. So no, account B will eventually surpass account A. All right, number 4. See, I can't guarantee that's chapter 1. Now I'm thinking that it's not chapter 1 anymore. I'm trying to think. Hold on. You know what? I have folders on file. Let me go to my stuff and let me find out what chapter that was in before I keep going. You know what I think it is now? I think it's section 4.8. I don't think it's chapter 1. I think it's chapter 4. Section 4.8 is titled Solving Nonlinear Systems of Equations, and I think this is more so that one. Chapter 1 does have exponential functions, but we compared one to a linear one. That's why I wasn't sure. That's what I think it is. Number 4. Your friend claims he can prove the parallelogram opposite sides theorem using the side congruence theorem and the parallelogram opposite sides congruence theorem. Is your friend correct? Explain your reasoning. Either there's a typo. No. Either there's a typo or it says proving a theorem with a theorem. No. You cannot use a theorem to prove a theorem. So your friend, you cannot use the same theorem. Your friend is incorrect. They cannot use a theorem to prove itself. It's like if I said define something that, define salt, and you say something that's salty. Something that has salt in it. Something that is salt. It's like it's like proving the alternate interior angles theorem, right? You have two parallel lines cut by a transversal. I have boom, boom, cut by boom. They're parallel. And I say prove it, and you say, given you have parallel lines, I can prove these are congruent by the alternate interior angles theorem. No, you can't prove the alternate interior angles theorem with the alternate interior angles theorem. You got to use corresponding angles, and then vertical angles, and then the transitive property and stuff like that. You can't use that. Now, what can you use to prove this theorem? Because it is a theorem. You can use you can use what we did here. You can use this top one. Prove the triangles are congruent here, and then by CPCTC, these sides will be congruent to each other, and these sides will be congruent to each other. So that's what you can use. You can say it's a parallelogram given. You can use alternate interior angles in the reflexive property and not side, side, side. So let me just say your friend can use angle side angle and CPCTC, however. So basically that. Basically that. That's out of this chapter, chapter 7. Chapter 7. Okay, number 5. You randomly select a vertex of polygon QRSTUV. What is the probability that the x-coordinate is greater than -3 or the y-coordinate is less than 4? Now, this would have been out of chapter 5, and I'll be honest, I haven't done chapter 5 yet. Statistics is one of those things that I have to re-study up on again before I do it, so it's likely I might stumble upon what this problem's asking for a little bit. I actually, I kind of forgot that chapter 5 would be a part of the stuff here. So let's take a look at what they're actually saying. You randomly select a vertex of this polygon. What's the probability the x-coordinate is greater than -3? Oh, a vertex. So a vertex is randomly selected. Okay, this should be fine. I thought they meant an area thing. So here are the 6 vertices. Now, let's label what they are before we keep moving forward. So Q is at -5, -2. R is at -4, 5. S is at -1, 6. T is at 2, 5. And the other thing is, although I know kind of how we can answer this one, I don't know the answer yet. I have to keep working. But although I have a version of how we can answer it, I don't know how the book goes about a problem like this as far as what they would do. So my process might look different from theirs. What I'm going to do is generate the set of all the x values that exist. Let's rank them in order so that we know exactly what's here. We have -5, -4, -1, -2. -5, -4, -2, -1, 1, and 2. No repeats, but if there were repeats, you'd want to write the repeats out. It's not just domain and range, but I am writing them in order to help myself out. Y does have repeats. It has 1, 2, 2, 5, 5, and 6. And like I said, it's important to list the repeats because when it comes to probability, there is more weight. When I say, what's the probability something's less than 4 or something like that, I think that's what they say. Literally, both these 2's count for that thing. So probability that an x coordinate that I select is greater than -3. What are numbers that are greater than -3? These guys. These 4 out of 6 right here. Probability that I select a y that is less than 4. I think these p's are supposed to be capitalized. See, the little things I don't really remember. Probability that a y is less than 4 are these 3. That 3 out of 6. Right there. Now, here's the part that I'm going to kind of be, Probability x coordinate is greater than -3 or the y coordinate is less than 4. What I have to do now is this addition. I don't know if I'm going to do this right to begin with. Probability of x greater than -3 or y is less than 4. It's going to be equal to the probability that x is greater than -3 plus the probability that y is less than 4. And we got to subtract the probability that x is greater than -3 and y is less than 4 because there is overlap for those things. And I'll show you which ones that they are when we get into them. X is greater than -3 and y is less than 4. Because, once again, there's overlap. There are some numbers where x is greater than -3 and ones that are y is less than 4, and they're being included twice in this. So this will be 4/6 plus 3/6, and now we got to take away the ones that are both the same together, greater than -3 and less than 4. This is not greater than -3 and less than 4, so not that one. Greater than -3 and less than 4, no. Greater than -3 less than 4, no. Greater than -3 less than 4, no. Greater than -3 less than 4, yes. Greater than -3 less than 4, yes. So we got to take away this 2 out of 6 here. that includes that overlap, and that'll be 5 out of 6. I got a 5 out of 6 chance that when I select, what is the probability the x-coordinate is greater than -3 or less than 4? I believe that that's how that thing works. So to show you how this thing... Now, listen, what I did was probably overkill for the problem, but it is something that works on how an OR condition works for items that are not... What's the word? Mutually exclusive, I believe, is what we say. That we got to take away this thing here. Let me show you and see that that actually does work. Probability... So, hold on. This is probability x greater than -3 and y is less than 4. And then let's also look at the probability x is greater than -3 or y is less than 4. As long as you satisfy just one of these, I should get a check mark on it. Is x greater than -3 here? No. Is y less than 4 here? Yes. There's one. Is x greater than -3 here? No. Is y less than 4 here? No. There's the one that shouldn't work. All the others should if we did this right. Is x greater than -3 here? Yes. Doesn't matter if y is less than 4 or not. X greater than -3 here? Yes. Doesn't matter if y is less than 4 or not. We know from these ands these are true. X is both greater than -3, y is less than 4, greater than -3, y is less than 4. That is a 5 out of 6 probability there when we look at that. So 5 out of 6 chance that when we select a vertex that would work out. And here was the math that also coincided with that. So either or seems to work in that kind of problem. This concerns me when I haven't done chapter 5 yet, that when I go back to do chapter 5, if I have like 80 questions like that in a section, that it's going to take a long time to do. So I'm really curious to see how the book goes about it. They're more than likely going to work it this way. And by the way, another way I could have done it is with the graph itself. Last thing I'm going to mention, not like that I could have done it, but that I could have imagined it. Let me show you the last thing here. Let's say that I did this. Let's say in purple will be all of the x values that are greater than -3. You have to keep in mind that -3 don't count, but there is nothing that's actually on -3. And then in orange will be all the y values that are less than 4, the ones that are underneath, like that. So you got to ask yourselves which ones do belong in either set. It is an OR. That's 1, 2, 3, 4, 5 of them. R is the only one that does not belong. So that's another way we could have done it, which is the fastest way to do it here based on having the graph itself. Okay, let's keep moving forward. We got 3 more problems to do. I got about 12 minutes till the hour mark. I wonder if I can beat it because some of these go kind of long. Number 6. Choose the correct symbols to complete the proof of the converse of the hinge theorem. Hinge theorem is out of chapter, I don't remember, chapter 6, I believe, with the triangle bits. Let me first copy and paste this into my set before I write down chapter 6. So this was, I don't remember the exact section, 6, 7, 6, 8, something like that. I don't know. Maybe there wasn't a 6, 7. Maybe 6, 6, but chapter 6. I'd be more likely to remember having made these videos, but I just don't. All right. Given AB is congruent to DE, and given that BC is congruent to EF, AC is greater than DF. So let me state out loud what the hinge theorem is all about. When 2 sets of sides are known to be congruent, we can determine the comparison of the measures of the included angle between these by the side that's opposite those angles, given that these two are the same. If this is greater than this one, then this angle measure will be greater than that one. So we're completing an indirect proof of the converse of the hinge theorem. Let's first assume temporarily that the measure of angle B is not greater than the measure of angle E, also known as less than or equal to. Then it follows that either measure of angle B is either less than measure of angle E or that it is equal to measure of angle E, if that is the case. So let's see what would make less than or equal to. If measure of angle B was, I guess less than, if measure of angle B was, by the hinge theorem. Let's try the less than. Oh, Less than or equal. See, I don't know which ones to fill out yet. I don't know if this is going to be equal or less than or anything like that. I'm not sure yet. But we are assuming that it's greater than. Let's start with less than and see if this works. If measure of angle B is less than measure of angle E, then AC would be less than DF by the hinge theorem, which would be true. If measure of angle B was equal to measure of angle E, then angle B would be congruent to angle E, or then it is, or then it would be. So therefore, by the side angle side congruence theorem, these two triangles would have been congruent to each other, and therefore AC would have been, the length of AC would have been equal to the length of DF. I don't really need to have these circled. Both conclusions contradict the given statement that AC initially was greater than DF. This one contradicts it with the less than. This one contradicts it with the equal to. So the temporary assumption, measure of angle B is not greater than or equal to measure of angle E, cannot be true. This proves measure of angle B is greater than measure of angle E. Sorry about that. That sneeze, maybe. Let me pause this. Let me drink some water because it's kind of hard to talk now. Hold on. Woof. Okay. Okay. Yeah. So, going back to this proof, they're saying like, hey, let's do the contradiction. They're saying prove it's greater than. Let's first say that it's not greater than. If it's not greater than, it's either going to be less than or equal to. If it was less than, AC would be less than DF. That ain't allowed because AC's got to be greater than DF. The hinge theorem would have said that. If they're equal to each other, then these triangles would be congruent. Therefore, these would be equal to each other as well. But AC's got to be greater than. So that contradicts both of those. So it must be, therefore, using the indirect proof. I'm not saying I prefer indirect proofs. In fact, they're kind of still new to me, using them and writing them out. I don't think I did them growing up. But in a way, that might be better to do than actual two-column proofs whenever it's used. All right, number 7, use the... Oh, we actually have to do a proof. Ooh. I was thinking in these things we wouldn't have to do any. I mean, outside of filling in blanks. Should I use an indirect proof? Use the isosceles trapezoid base angles converse. Ooh, mouthful. To prove that ABCD is an isosceles trapezoid. Oh, that's a lot, man. I got to figure out what I'm going to do with this one here. So... And that diagram is pretty small, but we'll just have to work off this. I didn't expect to prove. I don't think we're going to finish within the hour then. So statements. And reasons. Yeah, cumulative assessment. And this one's much more full board. Normally it's a lot of multiple choice and do the previous problem, which was fine. Fill in blanks, all that kind of stuff. Not so much here. This is an actual proof. And the bottom one's a proof, but it's filling in blanks, and I feel more supported. Because these ones, I'm like, I don't know what I want to say next. So BC parallel to AD is given. You can see that on the diagram. And then you also have these marked in the diagram. Angle EBC is congruent to angle... Yeah, you can see them. There's the double marked ones. ECB and angle ABE. These are the single arc? No. Oh, I'm sorry. Those were the single arc marks. This is the double arc marks here. ABE is congruent to angle DCE. This be given. All right, and it's all marked up. Okay, before we keep moving on, what's the base angles converse? Base angles converse, I believe, is the one that says a trapezoid with congruent base angles means it's an isosceles trapezoid. So proving it's an isosceles trapezoid, I think will pretty much be... I don't think we're just proving these two angles are congruent. I think we want to prove that these sides are congruent. In order to do that, probably going to go off to either go off congruent triangles, or because either these two triangles are congruent, or work off these parallelograms, if we could work off these being parallelograms. And we maybe can. Listen, I have this mark here. This alternate interior angles congruent thing I can do. I can do alternate interior angles congruent, and here I can do alternate interior angles congruent. Let me keep working off this. I want to see what else I have. either, can I do that side congruent to that? Is E a midpoint? Is there a way I can establish E as a midpoint? Or can I do this congruent to this because of isosceles triangles? Okay, I'm going to go off isosceles triangle stuff here. Let's start with these ones so I don't forget it so you can see it for what it is. So, okay, this proof actually might not be too bad. Inside this thing here, I'm going to say it straight up. I don't know if I need to use it or not, but triangle BEC in the middle, BEC is an isosceles triangle. It's an isosceles triangle because the base angles are congruent. Base angles of triangle are congruent. That works for me. If that's true, then that means that BE and CE are congruent to each other. This is the definition of an isosceles triangle. It has congruent legs. Iso triangle. Okay, so I got that. Now I have a set of alternate interior angles. Remember, these are parallel lines cut by a transversal. That means these are congruent. And then two parallel lines cut by a transversal here would mean these two are congruent. These are sets of alternate interior angles. I'm pretty much going to do them in one step. So that's angle, this is the top left, the small one, angle CBE, what do they use? EBC. Angle EBC is congruent to, and I'm gonna make markings here. So EBC, it's going to be congruent to this one here, AEB. I'll call it BEA. Angle BEA. And angle over here, BCE. No, they say ECB. Angle ECB is congruent to angle CED right there. CED by the alternate interior angle theorem. Remember, this is allowed because the lines are parallel. But really what I got to do now is mention these two are congruent to each other by the transitive property of congruence. Remember that that the EBC, these two are congruent to each other. So now I can say that these two are congruent to each other. Angle BEA, angle BEA. I imagine this is the way they'd want you to do the proof. It's congruent to angle CED. I don't know if I would have known to do this on my own. Transitive property of congruence. So now I have an angle side angle case with angle side angle for this triangle to be congruent to this triangle. I'm going to use different colors. In fact, I think I can use a triangle tool, which can stretch it out perfectly into there. Sorry if I mess it up a little bit. But I'm going to say that that triangle is congruent to this triangle here, like that. Okay? So now make sure you get parts that correspond. These triangles kind of reflect with each other here. So triangle, I'll call one ABE. Triangle ABE is congruent to triangle. Now I'm going to say DCE. Look where those are. DCE. This is angle side angle congruence theorem. Two more steps. Now by CPCTC, the corresponding parts AB and DC will be congruent to each other. So boom is congruent to boom. Again, these are the parts that correspond. So segment AB is congruent to segment DC by CPCTC. And that means this is an isosceles trapezoid by definition. ABCD is an isosceles trapezoid by definition of isosceles trapezoid, which has, it's like the same thing as definition of isosceles triangle. Two congruent legs. Isosceles trapezoid is two congruent legs. We already know it's a trapezoid based off the parallel sides. Okay, that's number 7. I have one more to do, number 8. One part of the rectangle diagonal theorem states, hold on, I'm bringing it up. Number 8 states, if the diagonals of a parallelogram are congruent, then it's a rectangle. Yes. Using the reasons given, there are multiple ways to prove this part of the theorem. Probably true for a lot of theorems. Provide a statement for each reason to form one possible proof of this thing. So based on the reasons, we're going to come up with what statements they're using, which is nice. They give me structure where I can work this thing out and not say, I wonder what they're going with. So this might be a quick one. Let's hope. Because then we'll be all done. Because I am 15 seconds to the hour mark. All right, we will surpass an hour. That's okay. All right, number one, it is given that QS is congruent to RT, given that the diagonals of this quadrilateral are congruent. It's also given that QRST is a parallelogram. They don't actually ever write that, which is interesting. By the parallelogram opposite sides theorem, we can also state, I mean, it's really interesting that they don't, with the given here, a lot of stuff is not mentioned. They're not mentioning diagonals bisect each other, because look, they're going straight to triangle congruence. So we're going to be stating two sets of triangles are congruent. And they said there's more than one way to do this, by the way. We can either prove these two triangles are congruent or these two triangles are congruent. They really gave us the option because they let us use our own letters here. They don't do anything beyond that. So let's do these triangles here, I guess, because why not? So if I'm going to do that, then I'm going to prove this. I'm going to show this is congruent to that, QT. Segment QT is congruent to segment RS by the parallelogram opposite sides theorem. Opposite sides of a parallelogram are congruent. So now these two triangles are congruent. Triangle, oh, is there a letter in the middle? I take it back. Without a letter in the middle, we're not doing that. I guess that's also why we haven't yet mentioned these are congruent to each other in that way. So hold up 1 minute. And I'm fine with doing what I just did here. This congruent to that. I'm missing stuff, though. They still don't... This isn't enough for side, side, side. Because I would need a third set of sides. I have two sets of sides here. Oh, I need to do two sets of parts. Probably. Let's do QT. Let's just do both. QT congruent to RS and QR congruent to TS. Okay. Do both of them. They just didn't really give me room. So now I can do side, side, side in whichever way I so prefer. These are congruent. But which triangles are now congruent? Well, you'd want to do one, and honestly, I don't know. I wish I kind of built this up a little more so. I can do either this triangle congruent to, let's say, this one. Boom. In which case I probably listed corresponding parts the wrong way. Or I can do it congruent to this one here, in which case I still probably listed corresponding parts the wrong way. I don't really know because we didn't do reflexive property. I want to walk through this better. There's a CPCTC, parallelogram consecutive. Maybe this is harder than I thought. This is not untrue to state this. I just don't know which ones we want to do yet based off congruent triangles. Let's see. What do we want to show? What are we trying to show? That it's a rectangle? Oh! I forgot. We didn't know this was a rectangle. So, right, it's a parallelogram. We need to know it's a rectangle. Okay, does that upset anything I said before? No, opposite sides congruent. The diagonals bisect each other thing is still something they haven't really brought up. That makes me concerned because I don't know which sets of triangles they want me to say. Okay, let me move down more to figure out what else I want to say here. Parallelogram consecutive angles theorem would show that angles are supplementary to each other. Congruent supplementary angles have the same measure. I wanted to say that before. Okay, so... Okay, I'm going to go off this one here. Let's say this triangle, let's call it QTS, is congruent to triangle RST. So the green and the blue, that would make this angle here congruent to this angle. QTS, angle QTS, this is CPCTC, is congruent to angle RST. And I do that based on the flow of what they say next. Now, angle, this, okay, so there's a lot that's kind of in the diagram. Let's kind of delete a lot of it. Now that we know that these are congruent, it was all a lead to say that these are congruent to each other. Now we're going to say that this big angle Q and this big angle R is going to be supplementary to that big T and that S. So angle Q I'm sorry. This is just weird. It's weird how this thing works itself out. I'm very sorry. They're missing a statement here. When I did this one, this triangle congruent to this one, if I did side, 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 I never said TS is congruent to itself because they never used reflexive property. Oh boy. I'm going to still work off this proof. I'm going to insert my own statement if needed. I apologize if I didn't do this by side, side, side and CPCTC. Because opposite angles are already congruent. I don't need to know that there. All right, I'm gonna keep working the way that I had before. So let's see if this works. Angle QTS and angle. There's not much room. Angle TQR are supplementary, and angle TSR and angle QRS are supplementary. The consecutive angles theorem for that. Now, congruent supplementary angles have the same measure. Now I can say that the big Q and the big R are congruent. So angle TQR and angle QRS are congruent. So those are now congruent. The double marks kind of indicated before. Parallelogram consecutive angles theorem would also then show that, oh boy, I don't know how to work out the proof the way that they want you to. There must be something that I'm missing here. Q and R are going to be... Okay, before I said supplementary, I'm going to say they add to 180 because they're saying subtraction property of equality now. So measure of angle... I'm getting this wrong. I'm getting it in a way that they wouldn't want me to do it. Measure of parallelogram consecutive angles theorem. These are going to also add to 180. Measure of angle, I'm just going to call it Q and R. It's the big guys. Measure of angle R equals 180 by the subtraction property of equality. If I subtracted R from both sides, is there a way that I know that it's 90? No. I'm not working this out the way that I want to. Let me think about this one. I really apologize. This probably isn't helpful for you. So let me think about it and get back to you. Okay. I think I figured it out, but I'm still iffy about the way that they pose something, which was the side, side, side part right here. So I'm still good on my triangle congruence. However, they never mention something like TS is congruent to itself by the reflexive property. This ain't side, side, side until that. So I think there's something else they need to insert. But the part that I think I messed on is, why do I want to actually show these congruent QTS and RST? It's this part, the congruent supplementary angles have the same measure. I looked at that wrong. I was thinking about that as two angles that are supplementary to two congruent angles are then congruent to each other. No. What we want to say more so is two angles that we found that are supplementary that are also equal in measure are both going to be then congruent or equal in measure, that they're both basically going to be 90. Because what we really want to get at is the definition. I looked lower, definition of a right angle, definition of rectangle. Definition of right angle are ones that are going to be 90 degrees. So what we really have to do is get into the math portion of this right here. So let me kind of break that down and see what I have again. And then we still got to reinsert. We got to get a reflexive property thing within here. It's missing, which is just bad. And even the things they marked up, it's just bad in what they did there, sort of. Okay, so parallelogram consecutive angles theorem. I want to talk about these two guys, basically, these two specifically, adding to 180. Not just being supplementary, but adding to 180. We have to get straight into the numbers of them. And if you don't mind, it's basically just the big angles we're referring to. So T and S. I'll call it that. Measure of angle T plus measure of angle S is 180. I know that's improper, but I'm going to go based off that. Now, congruent supplementary angles have the same measure. these are both supplementary to each other, but they're also congruent to each other as well, the T and the S. So both of these are going to be 90 degrees. This is part of my setup for this. Measure of angle S is measure of angle T equals measure of angle S, and they both equal 90. That's kind of the way that I'm going to go into that mindset of this thing. They're both the same measure, and they're both 90. We have to talk about right angles there. Now we have to get into the other ones that are also these guys, the Q and the R, the big Q and the big R, that these guys are also, they add to 180 together, but I want to say they add to, these are both 90 now. So I want to say that they both add to those being 90. So I'm just going to call it Q. Measure of angle Q plus 90 is 180 because they show subtraction property of equality. And measure of angle R plus 90 is 180. I'm guessing that I should have my own room and writing these things down and not filling it in this small blank, but that's what I have right now. By the subtraction property of equality, both of these are also now going to be 90. Measure of angle Q plus measure of angle Q equals measure of angle R, which is 90 because we subtracted, I mean, they're both the same, but they subtracted it and they're 90 degrees. By definition of a right angle, these are all 90 degree angles. Angle, the big guys, angle T, angle S, angle R, and angle Q are right angles. By definition of right angle, they're all 90 degrees, and therefore QRST is a rectangle. By definition of rectangle. So not all the reasons always work out the way you want it to. Obviously, they said there's more than one way to do it, and clearly there is. I used the bottom ones. I could have used the top ones. I used the left versus right. A lot of different ways. They are missing a reflexive property thing. I'd want to say that somewhere TS is congruent to ST by the reflexive property. If I want to truly use side congruence, yes, I needed QT congruent to RS. I never really needed QR congruent to TS, but I needed TS congruent to ST by the reflexive property for true side to side of the two triangles that I actually made congruent to each other. And I think that works itself out. I'm not going to say I skipped steps because they gave me the steps that were here. We did literally skip a step here. But making use of a reasoning like this, congruent supplementary angles have the same measure. I mean, how many times do I have to instead use substitution and definition of congruence and then divide by 2 by the division property? Instead, we can use just that right there. All right, guys, I spent much more time on that problem than I ever thought that I would. I apologize on that. Sometimes these things can be a little bit, troublesome. Even for myself, it just depends on the things we have on proofs. But that was the cumulative assessment of this. This was also the Chapter 7 test. So hopefully, listen, I like to do these on the fly, having not done them before. Even struggling through them, for me, I think is a good dialogue and conversation for you guys to make better sense of how you can answer these kinds of questions. Not just that specific one, but other ones along the way, right? Because you're not going to be tested on that exact question. You'd be tested on something else or whatever. So hopefully that made sense that we still did it like that, even if we struggled through it. And maybe you didn't have to look at this problem. But guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. We are done with Chapter 7 until we hit another cumulative assessment where we get another question on that. By the way, that would have been out of Chapter 7 as well. So Chapter 8 is to cometh soon with, I don't know how many sections there are, but I know it has to do with similarity. So let's have some fun on that later. Take care. I will see you in the next one.